This is section 2.2, and in section 2.2 we're talking about limits involving infinity. So to quote a favorite cartoon character of mine, we're going to go to infinity and beyond. Before we get started, being close to the beginning of the year, I just want to clarify what's happening in WebAssign when assignments come due and their due date passes. So for instance, if you notice, if I log in as a student, section 2.1 assignments are gone because they were due before the September 15th date. So if you didn't finish them, where they went is I extended them. They come down here to the bottom of the Unit 2 list. Notice Section 4 is the last section in the unit, so here's my 2.1 assignments. What I do is I extend them to the test day so that you can keep working on them. And so go ahead and keep working on them and get them to at least 100%, and that will meet your proficiencies for that section. If you didn't work on these because you want to take the proficiency quiz in Blackboard, a 3 or a 4 on that quiz will substitute for these homework assignments. So I'll still extend them. You can work on them if you'd like to, but I'll take your proficiency quiz if the score is good enough. So if we look here, they're down here now because, again, WebAssign sorts assignments by due date, and that's the day of the exam for Unit 2. Okay, if you do need to finish them, please don't wait too long. Okay, I would finish them up in the next day or two because we don't want to have to really be doing anything but testing on that day. Okay, so we keep throwing this question out at you. What does a limit do? It's part of our marking the text activity. So remember that a limit gives us a language, and that language describes our outputs or our y values as our x values approach a certain value. So that just allows us to express where our function is going. We started off the class period with our sketching a function activity, and I asked students to look at their posters and see if their poster had a horizontal asymptote. And if they did, I asked them to verify that asymptote, that they had written an equation for that asymptote. So remember, horizontal asymptotes have the equation y equals. And then if they didn't have a horizontal asymptote, maybe they had a vertical asymptote. And again, I asked them to make sure there was an equation next to that asymptote. And again, vertical asymptotes, they go up and down, so their equations are x equals. And the reason why I did that is because these asymptotes involve limits that go to infinity. So if you think about a horizontal asymptote, and we're going to write these two limit notations now with respect to those asymptotes. If you look at a horizontal asymptote, so it goes across the page, that means that your x values are going either towards infinity or maybe towards negative infinity. And as we go out to those x values, your y values are approaching some asymptote. So they're approaching some finite value. So here are the limit expressions for horizontal asymptotes. Vertical asymptotes, and if you notice, vertical asymptotes, as we approach some finite x value, we just go up to infinity. So the limit expression for a vertical asymptote is as we approach this asymptote, this finite value, our function values or our y values go to either positive infinity or maybe they go down to negative infinity. So we're now associating the asymptotic behavior of our functions with limits. And when we do that, notice the limits involve infinity. So that's what this section is about, is appropriately identifying those asymptotes. So here's our essential question. How can limits be applied to describe asymptotic behavior? So go ahead and get that written down in your essential question section. And so the first one we're going to talk about are horizontal asymptotes. So like we just said on the last slide, our horizontal asymptotes, okay, that is an equation. The asymptote itself is the equation y equals some number. We'll call it b. So horizontal asymptotes occur as x goes to either infinity or negative infinity, and the y values of the functions then get close to value b. And so the first function we're going to look at is 1 over x, which I think is a function you're pretty familiar with. 1 over x looks like this. As x gets big, 1 over x gets small. And how many of you realize that when x is negative, that 1 over x then is a negative value, so 1 over x actually has this look to it as well. So we call that rotational symmetry about the origin. And so we're going to look at the limits here. So first of all, we're talking about horizontal asymptotes specifically. Looking at the graph of 1 over x, we can see here's the horizontal asymptote. Its equation is y equals 0. And it happens to be a vertical asymptote as well. We're going to talk about that in some later slides, but for right now, we're just going to focus on the horizontal asymptote. So to find horizontal asymptotes, the strategy is take a limit of the function as we approach infinity. So remember that we have some special fractions from our previous lectures. We can take 1 over a big number, 1 over infinity, and essentially call it 0. Okay, and that's nice because it gets us out of doing a lot of the math. So that limit then must be 0. So as we go out to infinity on the x-axis, our y values are getting closer and closer to 0. When we're talking about horizontal asymptotes, though, as you notice from the function activity, sometimes the left side of the function behaves differently than the right side of the function. So we always have to check both ends. And of course, horizontal asymptotes are also called end behavior. We'll get to that in a little bit. So we're going to check the limit as x goes to negative infinity. So 1 over, I call these big negative numbers. I know on the number line they're really small numbers. That's how we refer to them. So if you think of this though as it's negative and it's far away from 0, so I'll call it a big negative. That leaves us with a really small negative number. So again, as we're trending in towards the left, towards negative infinity, our y values are also going to 0. So those are the this is describing the right-hand side of the function. This is describing the left-hand side of the function. They happen to be going to the same asymptote. That doesn't always happen, but in this case, it is happening. So our asymptote then is at these two y locations. So there's the equation for our asymptote, y equals 0. Just to go over, again, we went over this in section 2.1, but the properties of limits, we can add, subtract, multiply, and divide them. And that's true as we approach infinity as well, as approaching a finite limit. So you can look at those more closely in your textbook if you want to. Here's an example that looks pretty complicated, but this is the really nice thing about dealing with limits involving infinity. And that is, we get to take a look at this and kind of get out of doing the math by just looking at the magnitude of the numbers. So for instance, as x gets really big, that's what this is saying, as x approaches infinity, as x gets really big, how significant is this value adding 1 to a really big number? And the answer is it's not that significant. So we literally can ignore the plus 1. Okay, so we're going to ignore it, and we're going to rewrite this expression without the plus 1. And so this becomes a lot more simple now to evaluate. Now at this point, we can look at this, and we're not going to go back to this, because we've already said this is insignificant. We can get rid of it. We look at this and we ask ourselves, is there anything we can do to simplify that? And so now we're talking about, solid math process. So we can simplify the bottom because the square root of something squared is just that x value. So we're going to simplify it, and that's sound algebra. And then we're going to keep simplifying if we can. X over x is 1. So the limit then, as x approaches infinity, must be equal to 1, which means if we would graph this relatively complicated looking function, okay, we would have an asymptote, a horizontal asymptote, since we took the limit as x goes to infinity, that's our strategy, with a horizontal asymptote at y equals 1. This next example, we've dealt with sine of x over x, and I know if I asked you to draw sine of x in the air, you would draw something that looks like this. Just goes up and down between 1 and -1, and it goes on forever. And so that's just sine of x. So if you remember, sine of x over x has a big hill at the y-axis and then gets littler as it goes out to infinity, and then also gets littler as it goes out to -infinity. So so we have asymptotic behavior here. We're gonna confirm that by finding the limit of sine of x over x as x goes to infinity. Now this is just a little bit different. In section 2.1, we found the limit of this expression as x went to 0. Now we're looking out at the ends of the function, which means we're looking at something that's called end behavior, and I'll talk about that more formally in a couple of slides. So here's the sine of x over x. So we're going to try to get you familiar with this shape, just like you're familiar with just sine of x. So as we go towards infinity, you might see that the hills and the valleys get littler and littler because we're putting bigger numbers here, and we know this is just going between 1 and -1. So this ratio is getting smaller and smaller. So if that's the case, then we can just visually see that this limit approaches 0 and this limit approaches 0. So so we're going to actually formally prove that using the sandwich theorem. We won't use the sandwich theorem too much this year. In fact, we won't use it at all after we leave chapter 2, but this is one of the rare instances where the sandwich theorem really helps. So we know the sine of x, the numerator here, the littlest it can be is -1, and the biggest it can be is +1. Okay, just the numerator, just that sine function. So that means the top really can be rewritten with these two numbers. We know it's not going to go beyond those. And then we're going to just divide it all by x so that it looks like this. And then we know these limits on this one and this one. If we take a limit of this left expression, -1 over x, as x goes to infinity, that's -1 over a really big number. That's one of our special fractions. This whole thing ends up being 0. And if we look at 1 over x as x goes to infinity, we know that this number, again, 1 over a really big number, it's one of our special fractions, this is also 0. So what we're saying is, since this is always going to be in the middle, then if the littler expression goes to 0 and the bigger expression goes to 0, then the expression in the middle has to go to 0. So by the sandwich theorem, we know that the sine of x over x as x goes to infinity is 0. So we're going to use that then as one of our useful limits. So at this point in section 2, we have two useful limits involving sine of x over x that we can use as we evaluate other limit questions. So let's use that and evaluate this limit. So we see a sine of x over x pattern. The first thing we want to do is rewrite this so we can isolate that sine of x over x pattern. And when you have a plus or a minus in the numerator with a single denominator, you can split apart those fractions. And so we have a 5x over x and a sine of x over x, both going to infinity. And then our properties tell us that we can take the limit of this and the limit of that and just add them together. We can add, subtract, multiply, and divide limits. So we're going to simplify this. And so this first limit question is the limit as x goes to infinity is 5, and then plus the limit as x goes to infinity of sine of x over x. So we just proved this. We're going to use the results of that proof to put a number in for this. And so we know that the limit as x goes to infinity of the function 5 is just 5. Right? That's like saying when x is 1, y is 5. When x is 2, y is 5. When x is 3, y is 5. If I fast forward, I could say when x is 100, y is 5. When x is 300, y is 5. So this limit is just 5. And then this limit, we learned on the previous page, is 0. So our limit then for this entire function f of x is 5 plus 0, which is 5. Now let's talk about vertical asymptotes. Vertical asymptotes, the nice thing is that we know with vertical asymptotes we either are going to infinity or minus infinity. Okay, so either plus or minus infinity. The tricky part with vertical asymptotes is that we can approach the asymptote from the larger values, in other words the right side, or we can approach an asymptote from the smaller values, the left side. So we have to check both sides. So this is how you work with that. So this verbiage, I forgot about this verbiage here. As we approach our x value, and this is some particular finite value, our function value, our outputs, if we put it in our language, our outputs are going to go either toward infinity or minus infinity. So that's what that's saying. So let's go back and look at 1 over x. Now we're going to look at this vertical asymptote. So this is the example we started this section out with. We're going to look at this vertical asymptote. And if you notice, we're doing something different over here than we are over here. Our function values are definitely are going in different directions. So remember that when we're talking about vertical asymptotes, we're talking about where the denominator equals 0. Okay, so what value of x makes the denominator 0? That's just x equals 0. And from our special fractions, we know that if we have any number over 0, we can approximately call that infinity. Or we can say it doesn't exist, or I didn't put it here in the PowerPoint, but we can say it's undefined. So there's our vertical asymptote. So our vertical asymptote then involves a limit as we approach that asymptote, as we approach 0 from the positive side. So we have to look at both sides here. So as I'm approaching, here's 0, right? Here's x equals 0. As I'm approaching 0, as I'm going along this blue function, as I'm approaching 0 from the right, that's what the little plus sign means, from the right, or from the large values larger than 0, the limit of my function 1 over x is going from 1 over a number very close to 0, and that's also a special expression for a fraction. So 1 over a number very close to 0 is going to be a number that's very large. So this is going to positive infinity. And if we look on the other side of the asymptote, so just a comment here, if the denominator is positive, this whole fraction is positive, that's why it's going to positive infinity. If we look at the other side of the asymptote, now it's 1 over a number that's getting very close to 0, but it's coming from the littler values, the values littler than 0, and those values are negative. So 1 over a negative number that's very close to 0 is very large but negative. And so that must be going down to negative infinity. Remember, these are the y values. So this y value is going up to positive infinity. This y value is going down to negative infinity. So in this case, the denominator is negative, making that whole fraction negative. So this is, so a lot of times what happens on either side of the vertical asymptotes is that we have different things happening. So overall, we say then that since we got positive infinity, negative infinity, since these things are going to different values, then we just say that this limit doesn't exist, or this is the symbol for null set. I'm just trying to give you exposure to as many ways to write does not exist. Null set does not exist, undefined, all of those work. So let's take a look at a slightly different function, 1 over x squared. And so we know, and we're still talking about vertical asymptotes. So where is the denominator equal to 0? That's when x is 0. So that's where one of our asymptotes is. So we're going to look at that function. So notice it looks a little bit different. Because of the x squared, when we square x's, whether they're positive or negative values, we're going to end up with a positive value, which means both of these ratios are going to be positive, which means they're going to be up here in the first and second quadrants, those y values. So as we approach 0 from the positive values from the right, this gets to be, in fact, it goes very quickly because of the squared, 1 over a really big number. And, excuse me, we're approaching 0. 1 over a number that's really close to 0. I said that wrong. And 1 over a number that's really close to 0 is really big. The same thing happens on the left-hand side. Because of the x squared, this still ends up being a positive fraction. So in this case, the limit on either side of the asymptote is x equals 0, coming right down the center here. On either side of the asymptote, the function happens to be doing the same thing. So in this case, we can say that the limit as x approaches 0 is infinite. As opposed to the previous example where one was doing one thing and the other one was doing the other thing. We still could use the term does not exist. It's just a little less correct, but it would be accepted. Okay, so we've talked about horizontal asymptotes, we talked about vertical asymptotes. Now I want to talk about some specific terminology called end behavior. And end behavior, since it occurs out at the ends of your function, way out at positive infinity or negative infinity, we know that end behaviors then is just another way of saying let's look at the horizontal asymptote. Okay, and so end behavior models are, a model is something that we use to describe something. So here's a relatively complicated quartic function, right? Quartic is to the 4th power. So this looks pretty complicated. The question is, as x gets really big, we know that the 1 is insignificant, and really so is this term, the 43x. And really, if we're talking really big numbers, even this term, the 4x squared, is insignificant. So the question is can this model, g of x, which is just this term with the highest power, can that be a good model? And so the way we figure that out is we take a ratio of the two. And so let's take a look at what's happening with these two functions so that we can kind of get a visual picture. Near the origin, they're very different. But as we go out to x equal infinity, so I'm zooming out here. So this is zooming in. If you notice, the x-axis goes from -3 to +3. They look very different. But as I zoom out, and I don't have to zoom out far, I'm only zooming out from -6 to +6. Look how similar the two functions look. Okay, so just visually, it looks like this function f of x and this function g of x have the same y values. So if that's the case, then g of x is a good model. In other words, a good approximation. That's why we can ignore all the other terms except for the term of the highest power, which is kind of what we did in one of our earlier examples. We ignored the +1. So let's find end behavior. It's the same as finding our horizontal asymptotes. So here's my Buzz Lightyear making his horizontal asymptote. Okay. And the way we're going to look at that is we're going to look at two things. We're going to look at end behavior models that have the same model for both ends, kind of like that previous picture. We're going to use that previous example. And then we're going to look at end behavior models that have different models for either end. So let's take a look at this example that we've been talking about. From the picture, if you remember, on the left-hand side and the right-hand side, the 4x to the 4th matched f of x pretty close. So this model, 4x to the 4th, is a good model for both ends of the function f of x. So this is the test. If it's a good model, if this is a good model for f of x, then if we take the ratio of the two, if we take f of x over g of x and get 1, that means we have a good model. And then since we're talking about horizontal asymptotes, we got to check both ends. And so again, if we get f of x over g of x equal to 1, then it's a good model for the left-hand side and the right-hand side. Okay, and then the other thing is that there's also an asymptote there, because this is our strategy for finding horizontal asymptotes. That's what that bottom line is saying. We have an asymptote at y equals 1, because finding the limit as x goes to infinity and minus infinity is our strategy for finding horizontal asymptotes. So let's take a look at this. Is x to the fourth, 4x to the fourth, excuse me, a good model for this as x gets really big or x gets really small? So I realize there's not much work here, but again, as the x's as the values go away from 0, these become insignificant. The 1, the 43x, and the 4x to the fourth become insignificant, and we're left with 4x to the fourth over 4x to the fourth, which is 1. So we have a horizontal asymptote of y equals 1. This ends up being a good model. Okay, so what I want you to leave with is that is a comfortable feeling that it's okay when we're trying to find limits that go to infinity, limits as x goes to infinity. It's okay to start ignoring these terms that have either are just constants or powers that are lower than the highest power. It gets us out of doing a lot of math. So let's take a look at these two examples. I want to find the end behavior. Finding the end behavior just means we're taking the limit as x goes to infinity. And I want to find the end behavior for these two models. So let's take a look at this first model. So the highest power on the top is 3. So we're literally going to ignore the -1, the x, and the negative x squared. And we're going to rewrite the top as 2x cubed. And the bottom, as x gets really big, we're going to ignore the 5, the x, and the x squared, the -5. And so the bottom becomes 5x cubed. Now we're going to simplify. So we can cross out the x cubes, and we're left with 2/5. So the end behavior for this rational function is that we have an asymptote at 2/5. And that works for both ends. And the way we know it works for both ends is because these are both polynomial expressions. So let's try this rational expression to find the end behavior. So the end behavior, again, this is really informal. If you notice, I don't have any limit notation or anything, and that's okay. This is kind of your get out of math free card. We don't do it often, but for instances when x is going to infinity, we get to sidestep the math a lot. So let's find our end behavior here. So we can ignore the 1, the minus x squared, and the x to the fourth on the top, and we can ignore the -7 and -5x on the bottom. So we can rewrite this as just 2x to the fifth over 3x squared. So this is, these are examples of the highest power dominating. So if we simplify this, what happens is that we still have x to the x cubed, or x to the third power, in the numerator. So now we have to think about this, because we're really talking about putting in infinity for x. And so as we put infinity in for x, the top goes to infinity. And if the top goes to infinity, then it's not going to a finite value, which means there is no asymptote. So this one's just going up. We could call it unbounded if you wanted to, but it's just going up and up, and there's the values, the y values, are going to eventually approach infinity. And if that's the case, then there's no asymptote. There's no leveling off of those values. So when we're talking about polynomial expressions and we have a ratio of those, or we make it into a fraction, the end behavior is the same at both ends. When we start to get into expressions that don't involve polynomials, for instance, x plus e to the minus x, then if we look at this, we can see that we've got very different looking functions on the left than we do on the right. So if we look at this, you might see that on the right-hand side, as x goes to positive infinity, this looks like function y equals x, or g of x equals x. So if you look at this, if you look at the grid here, it looks like we're going up 1 over 1, up 1 over 1. So we have slope of 1, and if you extend this line down, we have an intercept of 0. So this really looks like a line on the right-hand side. But on the left-hand side, as we go to negative infinity, this looks like a curve. And so if we extend that curve, it looks like this. So it looks like e to the x. Now it's not following it as closely around the origin, but that's okay, because remember, we're really looking at it as it goes to infinity. And then it follows it pretty closely. So if you notice the expression, one side looks like this function, the other side looks like this function. And so this is a situation where the end behaviors are very different. So if you wanted to graph these three functions on your calculator, you could. You could put x in for y1 and e to the minus x in for y2. So those would be our two models, and then this would be our actual function. And this would be a recommended window for good viewing. Or just use this as a recommended window also. And so this is, again, there's not much math here, and we'll find a way of determining limits in a much more efficient manner later on as we learn a little more calculus. But as x approaches infinity, this really goes to 0. So this is the only thing that matters. That's why we know that dominates. So if this is the good model, then we'll take a ratio of that. So if x is a good model for the right-hand side, we're going to take a ratio of that. Remember, this is our model test here. So we're going to take a ratio of that. We could split it up, and then we could evaluate it. And that splitting up and evaluating is a pretty involved process. And right now, we're just going to gloss over that. We're not going to worry about the steps in doing the math here, because we actually do have an easier technique that we'll learn later. But we know it's a good model, we saw the picture, so this limit then has to be 1, because that's what happens when you have a good model. And then if we look at the other end, as x goes to negative infinity, then e to the x increases faster than just the regular value of x decreases. So e to the minus x is dominate. And so that becomes the good model. And so if we use this in our ratio for our model test, take our function over our model, and again, we're going to gloss over the math because we're going to learn an easier technique for things like this. We don't need to know it now. But since this is a good model, this limit also has to go to 1. So when we find good models, we know the limit of the function over the model is a limit of 1. The last example is finding all the asymptotes. So this last example is a combination of what we know about horizontal asymptotes and vertical asymptotes. So first we're going to do the horizontal ones, I think. So here's, and again, this is I'm giving you the graph, but we're going to do this algebraically. So the graph is just kind of a little bit of a help right now. So we can see visually that we have some horizontal asymptotes and we have some vertical asymptotes. Okay, we're going to go after the horizontal ones first. So what happens to this function as we go out to infinity and negative infinity, right? That's our strategy. Let x be big, get rid of small terms. So this is our end behavior, right? So our end behavior is really informal. So if we look at our function here, the 5 doesn't matter, that's small. The minus x doesn't matter, that's small. So the top is just 3x squared. Okay, at the bottom, minus 4 doesn't matter, that's small. So the bottom is just x squared. We're going to simplify. And so our horizontal asymptote is at 3. So there's our horizontal asymptote. Okay, for our vertical asymptotes, our strategy is to set the denominator equal to 0 and solve for the x values. So here's our denominator. We're going to set that equal to 0. We're going to factor this, x plus 2, x minus 2. And so we're going to get 2 vertical asymptotes. One is at negative 2 and the other is at positive 2. So there's our two vertical asymptotes. So this is a combination of the two things we learned today. How to find horizontal asymptotes, and knowing that horizontal asymptotes can either be thought of as end behavior, or it can be thought of as taking the limit as x approaches infinity and negative infinity. And vertical asymptotes is looking at just the denominator and doing what you did in Algebra 2 or pre-calc, and that is setting it equal to 0 and solving. So that really kind of summarizes what we did in this section. So let me just reiterate that. Horizontal asymptotes, we let x get really large or really small. We take the limits as x approaches positive infinity or negative infinity. We also can call this end behavior and use our end behavior approach. How do you determine vertical asymptotes? You let the denominator equal 0 and you solve. And the vertical asymptotes, the limits always will be plus or minus infinity. Right? As we go up against those vertical asymptotes, our function is either going up forever or down forever. So at this point, you can do the homework. The homework has two parts, day 1 and day 2. I don't usually give you 2 web assigns in one evening, but this is one of those very rare instances where I do give you 2 assignments for one evening. Or if you're looking to test out of doing the homework, you can take the proficiency quiz in Blackboard.